Hi class, welcome back to Computational Tools. In this fifth MATLAB tutorial, we are going to explore generating animations in addition to nesting and indentation in MATLAB. So to begin, of course, save your tutorial with your name. And let us begin with animation. There are two simple ways to animate a plot in MATLAB. First, if the computations are sufficiently quick, the standard plot function can be employed in a way that the animation can appear smooth. Here is a code fragment that indicates how a for loop and standard plotting functions can be employed to animate a plot. So what we're going to do is we're going to create an animation with standard plot functions for some j from 1 to n. We're going to have our plot commands, and then we're going to end it. That is our syntax. And because we do not include hold on, the plot will refresh on each loop iteration. Through judicious use of axis commands, this can result in a smoothly changing shape. There are special functions, getFrame and movie, that allow you to capture a sequence of plots and then play them back. As the name implies, the getFrame function captures a snapshot or a pix map of the current axes or figure. It is usually used in a for loop to assemble an array of movie frames for later playback with the movie function, which has the following syntax. So we have movie, and then M is equal to the vector or matrix holding the sequence of frames. N is an optional variable specifying how many times the movie is going to be repeated. And FPS is also an optional variable that specifies the movie's frame rate. So if it's omitted, the default is 12 frames per second. So here's a code fragment that indicates how a for loop along with two functions can be employed to create a movie. So we begin by creating an animation with getFrame or movie. So for j equals I to n, we have our plot commands, and then we end and we play the movie M. So each time the loop executes, the movie commands create an updated version of a plot, which is then stored in the vector M. After the loop terminates, the n images are then played back by movie. So let's give it a shot. What we're going to do is we are going to create an animation of projectile motion. So we're going to try out an example problem. In the absence of air resistance, the Cartesian coordinates of a projectile launched with an initial velocity, so v0 or v0, so not naught, and angle theta naught, so the naught is usually used for to signify initial conditions. They can be computed with x is equal to v naught times cosine theta naught times t. Okay, so x, so our theta references the x-axis, so taking cosine of our magnitude gives our x component, and sine gives our y component. And for y, we also are dealing with the acceleration due to gravity, which is why we're subtracting off that 1/2 gt to the second. And t is time in seconds, of course. And g is the acceleration due to gravity. So we're going to develop a script to generate an animated plot of the projectile's trajectory, given that v0 is 5 meters per second and theta naught is 48 degrees. So let us begin by just clearing everything. So I'm just going to copy and paste all this and talk you through it. And it looks like it's on here twice, so I'm just going to uncomment that last piece. So we're going to clear everything. And then we have G is 9.81, theta naught is 45 degrees, and we're converting it to radians. So we have pi times 180 there, and our V initial is 5 meters per second. And so we're setting our first element of t, so that's our time vector equal to 0. So we're starting at time 0, and we're specifying that we're also starting at x and y equal to 0. So we're beginning at the origin. Now we're going to start with our initial plot. So our first plot is we're just going to plot x and y, and we are going to make them that open circle marker with a blue face color, size 8 marker size. And then we're setting our axis as extents. So x is going to go from 0 to 3, and y in this case is going to go from 0 to 0.8. And then we're setting M1 for our matrix M. And so M1 is get frame. So that's our start. We're going to show our initial plot. And we're going to set a time step. So that's our dt, that's our change in time, equal to 1 over 128. And so notice all of these, each of these lines ends with a semicolon. And so what's happening there is that, right, we're just suppressing it. We're not sending any of this to the command window. And now we have our for loop. For j is equal to 2. So starting at 2, ending at 1,000. So j is a vector going from 2 to 1,000. So for t of j, so notice that we started our count for our element, for our vector. Our first element, we started count at 2 rather than 1 because we've already defined t of 1. Our initial time is 0. So now we're looking at element 2. So this is t of 2, since t of 1 is already defined up above, t of 2 is equal to t of j minus 1. So if we're starting at 2, that'd be 2 minus 1. So it's equal to t of 1, which is 0, plus our time step, which is dt. So we're stepping forward 1 over 128. So this is another way to do this rather than doing the by. So having that extra colon with by is setting up this time step. And this is a pretty common way to run for loops. And so x is going to be equal to v naught, which is 5, times cosine theta naught, which is 45 converted to radians, times our time. So this time changes, right, as we step forward. So this is t of 2. Okay, so t of 2 is going to equal 1/128th of a second. And same thing goes for y. And so then we want to, after each time we run through this, we want to plot x and y because we want to show the projectile moving over time. So we have to show it one frame at a time. So each plot is a snapshot, and then we're going to play those plots over and over so it looks like an animation, so it looks like a movie. And we also want to fix our axes extents to match our initial so that our axis isn't shifting, because then the movie won't play smoothly. And so you need to make sure that your axis extents are defined. So once again, we're going from 0 to 3 in the x and 0 to 0.8 for the y. And so then for each element, for each j, we're going to get the frame. Okay, so we're playing the movie. So if y becomes less than or equal to 0, we want to break and end because we're showing a projectile. And so that projectile is going to stop when it hits y equals 0, when it hits ground surface. We don't want to see it continue on below the ground surface. So we're telling, so we're specifying where we break and end this loop is going to be when y becomes less than or equal to 0. And we all know it's going to be basically when y is 0. So then we're going to pause and then we're going to play the movie. So, and we're specifying n is 1. All right, so let's try it. So it'll pop up in a figure. Mine froze a little, but there we go. There's our projectile. We can replay it. So we're only playing it once. We can play it through multiple times if you change n is equal to 2 or 3. And my problem is I shoved this in the background so you can't see it. Hold on. So this isn't working well. Hold on. So let's try this again. Sometimes takes a minute. So mine is frozen. So I'm gonna, there we go. So it should play through 3 times. anyway, what happened here, let's try it again. So I keep having to break the function. So if you hit Command dot or Control Enter in MATLAB, it'll break it and play again. So it's a little buggy because it uses a lot of memory to do this. And so what I'm going to do is I'm just going to comment this whole thing out so that the rest of my code doesn't get stuck. All right. Because it'll just keep trying to replay that. And as you can see, I keep having to break the code and break from running the code in order for it to not freeze. Several features of this script bear mention, so let's summarize yet again. First, notice that we have fixed the ranges for the X and Y axes. If this is not done, the axes will rescale and cause the animation to jump around. Second, we terminate the for loop with the when the projectile's height falls below 0. When the script is executed, two animations are displayed. We've placed a pause between them. The first corresponds to the sequential generation of the frames within the loop, and the second corresponds to the actual movie. So let's move forward to nesting and indentation. We need to understand that structures can be nested within each other. Nesting refers to placing structures within other structures. We'll illustrate this with another example. The roots of a quadratic equation, f of x is equal to ax squared plus bx plus c, so an example of a quadratic equation, can be determined with the quadratic formula. So x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. That's probably permanently burned into your brains. So let's develop a function to implement this formula given the values of the coefficients. And we're going to employ a top-down design. This provides a nice approach for designing an algorithm to compute the roots. It involves developing the general structure without details and then refining the algorithm. To start, we first recognize that depending on whether the parameter a is 0, we will either have special cases, so single roots or trivial values, or conventional cases using the quadratic formula. This version can be programmed by generating the following function. So open up a new script and let's copy and paste this quadroots function into it. And then we'll talk through what's going on in the function. So let's delete my comments in these single quotes. All right, so once again, our function is called quadroots, and what we're doing is we're inputting values for our coefficients, A, B, and C. And our inputs are going to be A is the second order coefficient, B is the first order coefficient, and C is the 0 order coefficient. Our outputs are going to be the real part of the first root. There's going to be an imaginary part of the first root, a real part of the second root, and the imaginary part of the second root. So if A is 0, that's a special case. So if A is 0, and see how it's nested here? See how it's indented? So this is still part of this A is 0. So now as a subroutine to this if, we have a secondary if A is 0 and if B is not 0, then we have a single root. That's given R1 is equal to minus C over B. Else we have a trivial solution. So if B is 0, for example, then we have a trivial solution and we have try again. So then we end that piece. Else, so if A is not 0, we use a quadratic formula where D, which stands for discriminant, is equal to B squared minus 4AC. So if D is greater than or equal to 0, we get the real roots. So root 1 is minus B plus the square root of D over 2A. root 2 is going to be minus b minus the square root of d over 2a. And then we have the complex roots. And the complex roots are given as follows. Root 1 is minus b over 2a. I1 is the square root of the absolute value of d over 2a. Root 2 is going to be equal to R1, and I2 is minus I1. All right, so let's run this. Okay, and what we're going to do is, now let's try it. Quad roots of 1, 1, 1. Hold on. Yeah, see, even though I commented this out, it was trying to do this again in the background. All right, so let's try again. So I'm having these, okay, I keep having to break this. All right, here we go. So command dot or command enter can be very helpful. All right, so here we go. Here's our quad roots. And it might have run through a couple times because I kept hitting it. Yeah, it ran through a bunch of times. Okay, so now we can keep going. Okay, and you can keep trying, and you can do show the output for the rest. And now let's try anonymous functions. These allow you to create a simple function without creating an M file. They can be defined within the command window with the following syntax. So you have your function handle, or your F handle, is equal to @ so that's for your anonymous function, and then your argument list and your expression. So this is like a really quick way to write a function within your regular script without creating a whole nother function file. So fhandle is equal to the function handle you can use to invoke the function. Argument list is a comma-separated list of input arguments to be passed to the function, and expression is any single valid MATLAB expression. So let's try one. Let's call this one F1. So F1 is going to be our function handle, and it's going to be defined by, so we have to do equal @ our inputs are x and y, and our expression is going to be x and y. And our expression is going to be x squared plus y squared. And I'm going to suppress it. And so now you see that we have a function in our workspace. All right, so this little anonymous function is now in our workspace. So it can only be called from this workspace. It's not, it doesn't live in our folder like a regular function.m file. So let's try performing this with inputs 3 and 4. So x equals 3, y equals 4. All right, there we go. Aside from the variables in this argument list, an anonymous function can include variables that exist in the workspace where it is created. So for example, we could create an anonymous function 4 times x squared by typing the following. So if we do a is equal to 4, b is equal to 2, our second anonymous function is just going to require x as an input, and we're going to do a times x to the b. And let's do f of 3. So in this case, a is available in your workspace, so it's just the function is calling the a from your workspace, and b is also in your workspace, so it's calling the value of b from your workspace. The function handle holds a snapshot of the function at the time it was created. If we want the variables to take on values, we must recreate the function. Now let's look at function functions. These are functions that operate on other functions which are passed to it as input arguments. The function that is passed to the function is referred to as the passed function. Let's try a simple example using the built-in function fplot, which plots the graphs of functions. A representation of the syntax is fplot, or that your input are the function and the limits of the function. And so the limbs are going to be an xmin and xmax, for example. And for this case, func is the passed function. This function is smart in that it automatically analyzes the function and decides how many values to use so that the plot will exhibit all the function's features. Here's an example of how fplot can be used to plot the velocity of the free-falling bungee jumper we've been working with in our examples. So we're going to type this out. I'm just going to uncomment. Okay, so velocity, okay, so vel is going to be our handle for our function, and our input is going to be time. And see the the ellipses there? So that's telling us that, well, this is continuing on to the next line because our function's kind of long, this square root of g, which is 9.81 meters per second squared, 68.1 will be our mass, 0.25 will be our drag coefficient, and onward. And so the only variable we have in here is t. G, well, G is going to be constant anyway. M and drag coefficient are going to use the defaults here. And so we're going to plot the velocity for t going from 0 to 12, okay, our limits. And there it is. Okay, and so we have velocity and we have time. Recall that the full form of our terminal velocity is the following. V of t is equal to the square root of g times m over cd times the hyperbolic tan of the square root of g times cd over m times t. So using m equals 68.1 kilograms and cd equals 0.25, we can compute the average value of the function. So let's try it. Let's say t is going to be linear space. So we're going to go from 0 to 12 in even increments. And I'm just going to copy and paste our equation for v. And we want to find the average velocity. So we're going to use the mean function. Oops. Mean. I'm just going to undo a few things. There we go. Mean velocity. So the average you get is 36.087. So if you look at your plot, and that's somewhere in the middle, right? So that's about what you would expect. That seems to be a reasonable average. So always try to think through what you're looking at on your plot. So we have our terminal velocity, which levels out, right, over time. And here we're going from 0 to 12 seconds. So now let's write an M file to perform the same computation. So open up and generate a new M file and copy and paste this function. So, of course, I copied a little too much there. We have to start with function. And our function is going to be called func average, and our inputs are going to be a, b, and n, where a is the lower bound of the range, b is the upper bound of the range, and n is the number of intervals. And our output is going to be f average, which is the average value of the function. So x is going to be defined by the linear space function, going from a to b with n intervals. Y is going to be our function of x, and f average is going to be mean y. So let's give this a shot. So try running the function 0 to 12, 60 increments. And so you notice that the average velocity is slightly different because we have more increments here. We have higher resolution. Now let's rewrite the M file so that rather than being specific to the function, it evaluates a non-specific function named f that is passed in as part of the argument. So generate a new M file. And this one's going to be called funcaverage2. So on comment, and this time, f is the function to be evaluated. So we actually have to put the function as an input for this one. So let's run this. Okay. So because we have removed the subfunction func, this function is truly generic. And it can be run with the following command. So what we can do is we have our velocity handle and we have our equation. And so then we're going to run the funcav. There we go. There it is. All right, and then try it with sine on your own and describe whether or not the function makes sense. And then once you finish that, on your own, you're going to develop a function to produce an animation of a particle moving in a circle in Cartesian coordinates based on radial coordinates. Assume a constant radius r and allow the angle theta to increase from 0 to 2 pi in equal increments. So just remember how to convert an XY Cartesian coordinate system into radial, right? So we have a radius times the cosine of theta gives you the x component, and a radius times the sine of theta gives you the y component. So keep that in mind, of course, when you are writing your function. So that is it for the 5th tutorial of MATLAB, and I will see you next time for tutorial number 6.